I'm WalterHolemans, the Chief Engineer and Founder of the Planetary Systems Corporation, and I'm here to present on the lessons learned flying science mission on one of our new products, the Canisterized Satellite Dispenser. On 29 September of this year, a 3U CSD dispensed 3 spherical satellites called POPACs, and their science objective was to measure the atmospheric density change due to coronal mass ejections as a function of the decay of the orbit of these spheres. They all have the same coefficient of drag, so you throw up 4-inch diameter aluminum spheres with 3 different ballistic coefficients, and pretty soon they'll begin separating from each other in their orbital plane, and their orbital planes will begin to change. And so you can, for a relatively low budget, you can get a pretty good idea of how the upper atmosphere expands very rapidly in response to a coronal mass ejection. So it's very good science on the cheap, which was good because when I was approached by the principal investigator, he said he absolutely had no money. And if anybody here knows Gilmore, he's very good at getting free services from anybody he talks to. But his vision was borne out to be correct in that we could do it cheap. And there, the picture on the right is taken from a video from a amateur telescope that was tracking the sphere as it went over the sky. So we now know that all 3 spheres are operational and the mission is underway. It wasn't a perfect mission. I want to tell you some of the things that we learned. My video is not working, but let me just tell you, it was an awesome video, and we can show it to you later. So here are the 3 spheres inside of the CSD. We've got some O-rings that touch the spheres. They have to be very, very shiny. So we used polymer O-rings to bound the spheres. And then we had spring plungers pushing on the spheres so that when this entire package on the upper right was released from the CSD, it would automatically, those spacers would automatically let go of the spheres. It's kind of like an egg carton coming undone on orbit to let the eggs out, treat them very fragilely. One of the things that the CSD was very good at was applying the load shown on the tabs. So we could, once we put the entire loosey-goose package into the CSD and closed the door, all of those 4 spacers adjoining the 3 spheres would be clamped down very rigidly, make them very easy to model, and prevent the optical surfaces from being marred by jiggling as it ascended into orbit. So the first lesson we learned was that with 7 objects coming out of a CSD, each of which has 6 degrees of freedom, it's very difficult to predict what's going to happen. But it's essential to know it. If this was a $20 million mission or a $200 million mission, it'd be very important for the principal investigator to understand what the initial conditions are. Like, did the spheres come out, first of all? What was the relative velocity to help establish the initial orbital parameters? And did any of the spheres stick to the spacers? There's always that concern that if the spheres are sitting compressed adjoining the O-rings for several months while we're waiting for launch, will the O-rings somehow adhere themselves to those optical surfaces? One of the better ways to verify that it would work would to go on a vomit comet and employ some IMUs to measure the different rates of rotation of the bodies that we're ejecting. The other thing to do is to have a camera on the CSD looking in the direction that the payloads will deploy, and simply using several still pictures or even video to determine what the initial conditions are. Of course, we had a very low budget, so none of those things was possible. The second thing we learned was that is whenever possible or practicable, isolate the payload, whether it's a single CSD or a whole package of dispensers, like a whole payload isolation. I think Joe Maley can speak at length about that. In this case, SpaceX supplied some isolators. They supplied that whole bracket, and there's the flight CSD with Popax on it, and these are basically COTS isolators. And they did two things for us. They literally decreased the shock and the vibration that was going into the Popax structure, but they also bought us a lot of margin on the cheap. It's expensive to understand exactly what a flight random vibration environment will do to a payload. So if you don't have a lot of resources to do that, and isolation is cheap, well, you'll get a very good payoff for isolating. But for, we had the optical surfaces that are necessary to see the spheres from orbit. We don't want to mar those, but we also anticipate when we're going to the moon that people are going to fly ever more sophisticated optical payloads. And I've seen some presentations yesterday on ion thrusters. Some of those technologies look like they may be very sensitive to shock or vibration, not from just space flight, but from either the acceptance, proto-flight, or qualification process. So if those new instruments are not terribly well understood and you're constrained by budget, then one of the easiest things to do is to choose to isolate. And this chart shows the input in red coming from the launch vehicle, or at least this is NASA GAV's qualification limit, or I should say mil standard 1540. And here's the response at the payload. And you can see in the frequency band that these smaller instruments are sensitive to where they would resonate. The input into the payload is in some cases attenuated by 3 or 4 orders of magnitude. So you can imagine, say, an optic that might go off at 1,000 hertz. So at this level here, you're getting about almost 2 orders of magnitude less input than you would otherwise get. So no doubt that that's going to buy a lot of margin for some sensitive payloads. The third thing we learned was when the mission, we didn't know for several weeks that the spheres had come out. There was a lot of it was SpaceX's first flight of that variant of their rocket, and they had a lot of things going on, and they didn't have a lot of time to attend to what we needed. They didn't have the camera pointing in the direction of the Popax spheres, and because of budget constraints, we could not afford to procure the telemetry for the occupancy switch. So when the CSD dispenses a payload at end of stroke, a switch opens circuit. If we'd had that telemetry, we'd know, well, the payload's out. We had to wait a couple of weeks before some radars, some government radars, measured the 3 spheres and the 4 spacers adjoining the spheres. If this was a science mission where we had to start the mission within minutes or days of dispensing, that would have been a critical flaw to not know what, are these spheres out? We couldn't, Gilmore couldn't find them. Like we're in orbit, and to my surprise, we couldn't find the spacecraft. They don't, they're just dumb spheres. They don't have a beacon on them. You had to find them optically, unless you had the U.S. government's radar systems. So it turns out they found them. Things are going great, but it was a tough couple of weeks for all concerned. So now I'd like to go into a little bit about Planetary Systems Corporation, because I've heard a lot of talk about the 6Us and so on. What we started doing about 4 years ago was developing this whole family of dispensers. We've got a 3U through a 27U, and thank you. And what we're finding out is that the 6U is a very popular size for the DoD for their operational use. Originally, their need was to be able to build a space to integrate a payload to a launch vehicle within minutes. They wanted to be operationally responsive. So they said they want a box that an airman who's in a bad mood, that's sleep deprived in a loud building that's poorly lit, will still integrate a payload flawlessly. They wanted it to be that good. No tools, no written instructions, no QA. And so we wrote all the instructions, we engraved them on the box, and we deleted all permutations, or so we think, of installing the payload into the box. And we'll do a demonstration at the end of my talk. That took an enormous amount of work. The first concept worked very well, but not good enough. It wasn't meeting that specification, so we spent another 2.5 years and a princely sum getting this box to be extremely easy to use, extremely easy to test, especially for the end users. So no pyrotechnics, a DB9 connector to initiate it, a bunch of 9-volt batteries to supply the power so people could get familiar with the technology and determine whether they had any snagging hazards or something was missing. The other thing we spent a heck of a lot of time on with the greater community was developing standards and understanding how they might use them. The previous talk from ULA touched on a lot of these applications, especially dispensing from ESPA structures. One of the things we saw was a lot of folks were building auxiliary structures. They would go from ESPA to an auxiliary structure to dispensers. And so they'd have to go through the expense of that auxiliary structure. And that's why we populated the sides of the CSD with all these bolt patterns so that end users could simply manufacture the simplest possible auxiliary structure. Here's an example of 16 6Us dispensing from the volume between a primary payload and a thrust cone. Here's an example of a 12U that's dispensed from a geostationary spacecraft. So I talked to some large aerospace companies yesterday in the neighborhood, and they said they're very eager to supply this kind of service. So they seem to think it's a very good idea to dispense spacecraft from geostationary orbit. There's a talk about thermal problems that these smaller spacecraft might have. One of the considerations is you can just put MLI around these things, and again, we populated the side of the CSD to accommodate that, and then there's a lot of folks, to my delight, that are deploying small spacecraft in very close proximity to the space station. With that, there's another video I can't show you, but we can show you later. And then Ryan Williams will come up on stage. He's my coworker, and we've brought a 6U with us. And for the sake of driving the idea home, we'll go ahead and just deploy it on top of the podium. So this is our qualification unit, and now it's our demo unit. It's been through qual about 3 times as we refine the design, and it's electric motor driven. And do you want to deploy it up or sideways?
Sideways.
Okay. Okay. So we haven't practiced this, so you're going to give us a countdown from 3, and then on 0, I'll catch it. I'll do the countdown. Okay. So everybody's ready? All right. Cameras rolling. Okay. So, okay. So on 0. 3, 2, 1, 0. So here's a mock-up. Thank you, of the spacecraft. It's again part of the qualification unit, and one of the things we designed in was the capacity to constrain deployables with the CSD, and the utility of that is that it unburdens a limited budget in science from having to design a constraint mechanism for this and a release mechanism. We have roller bearings that bear upon specifically machined-in surfaces into the CSD so that the payloaders can focus on their mission and they don't have to allocate a lot of resources, especially risk, to their mission. So, do you want me to reinstall it? Okay. So, integration. I hope so. All right. So there. So that's ready for space flight. That's ready for vibration. That's always what we did before we did shock testing or vibes. So we're absolutely certain that it works. And we hope that it's these kinds of technologies that will greatly lower the price of you all executing your science missions so that you can spend your very limited resources on the fun stuff. So with that, are there any questions? Thank you.